Thank you. I'm Fei. I'm a first PhD student here, so I just got here, so I'm a little bit nervous, so I'll go quite slow across it. Today I'm going to introduce my project measuring earthquakes across the global continents from space and seismological observations. Here are some key points and outlines. First, I will give an introduction about what is satellite radar interferometry, and then about my project, then my current experiment and studies. The first I'm going to introduce is the electromagnetic spectrum. Currently we are very familiar about the optical images. The optical images is used visible light to acquire the images about here. The wavelength of the visible light is about 400 to 700 nanometers. But now what I'm going to use is the microwaves. So the wavelength of the light would be 2 centimeters. So currently we mainly use 3 bandwidths, the C band, X band, and L band, which approximately 24 centimeters, 6 centimeters, and 3 centimeters long. So I'm going to introduce the synthetic aperture radar. The traditional radar set, the image size is proportional to the wavelength of the antenna. However, synthetic aperture radar plays a trick. It uses a Doppler shift of the radar returns to the local ground points. So the image pixels is around 5 multiple 20 meters in size, and the antenna size is much smaller than the possible with the stationary antenna. For example, in the traditional way, to reach such image size, it would be known to kilometers long, that antenna. But for the synthetic aperture radar, it only takes for few meters. Like you can see the picture of the first InSAR satellite, the ERS-1. So yeah, it can use a very small antenna to reach a high resolution pixels. So let's compare some of the InSAR images with the optical images. The left side is the InSAR images, which is the original data is actually a complex data. It contains both imagery part and real part, or the amplitude and the phase. We can first see the amplitude images, which is very similar to the optical data. We can see here is the pore, and here is the same pore. And well, for the single InSAR images, the phase is very noisy. And you can see can't see any clear images here. However, when you use 2 images, we come to the interferometric InSAR, it would be different. The principle of InSAR comes from the classic double slit experiment. We are very familiar with this experiment. From here, the light source cross 2 slits and generate fringes in the screen, while the InSAR is very similar to this. First, the first satellite, he acquired an image, and after a few days or a month, it acquired the second images. Then it will combine the phase to generate the interferogram. We can see this case. The first InSAR image is generated in 2000 November 11th, and the second one acquired after 6 days, and drop the amplitude of the images and only use the phase to generate these interferograms. Here is the interferogram of the earthquake happened in Iran in 12th November 2017. The magnitude of this earthquake is 7.3. We can see this is here should be the center of the earthquake, and we can see many fringes here. The first one, second one, third one, and fourth one. Each fringes represents the deformation of the 24 millimeters deformation. So if we said the first here is 0, and the second one is 24, the third one is 48, and go on. So the more close to the center of the earthquake, it means the deformation is larger. And another technically we are using the seismology. Seismology is the study of the earthquake and seismic waves that moves through around Earth. We know each time the earthquake happened, it will release energies and will generate waves across Earth through itself, and the seismology will receive these waves and tell us about the information about the earthquake, like how large its earthquake to be and where the position and the time of the earthquake. So my project is we are mainly use the InSAR observations and complement with GPS and seismology to help to detect and measuring the earthquakes. The object of this project is to use Sentinel-1, the latest SAR satellite, to measuring the surface deformation, which associate with moderate-sized shallow earthquake across global land masses. And then I will model this earthquake to provide some basic parameter force and determine any systematic or region-specific belts and generate uncertainties. The project will improve our understanding of the small or shallow earthquakes, because currently our main studies are focused on the large, very large, like I showed, 7.3 large earthquakes. But this project is mainly focused on the moderate, small earthquake, like 5 or even smaller, that large earthquakes, so that we can improve our understanding of how the stress is transferred through the Earth and how earthquake is happened. And maybe it can help to predict the earthquake and may help to assess the damage of the earthquake and help to prevent it. The first thing we need to do about this project is to detect earthquakes. Not all the earthquakes can be seen under interferogram. Here we show some examples. In the first one, we can see there's a clear loop in the center of this image, so we can see it is an earthquake, and we can see it on the interferogram. And while the second one is a little noisier, and we can't see where the earthquake is, mainly because the noise, the atmospheric noise, the main noise source of the InSAR. And about the third one is completely noisy, and we cannot see any single of the earthquakes. And the second thing we are going to do is the earthquake modeling. Here is the concept view of the deformation of seismic circle. First, the ground deformation will generally it will follow a linear deformation and with a slow change. And suddenly an earthquake happened, has a huge deformation. It's jumped to here, and then it will slowly decay through the post-seismic, we call post-seismic. It will slowly decay, and finally it will return to the first case, like a low change or small change, and after for many years or even hundreds of years, it again happened as another earthquakes. So basically it is a circle. So my methodology is going to use the InSAR time series analysis. First, I have shown the single interferogram, and now since any two of the SAR images can form an interferogram, so we are going to use multiple combination of SAR images to generate an interferogram. You can see this figure, each blue dot on the figure means one image, and the line between them means generate an interferogram. So when we use multiple SAR images, we'll generate multiple interferograms. We can get a time series analysis of it. So here's my workflow. The first one, we will get many interferograms, and then we do some corrections. There are many noise, and then model the earthquakes. Finally, we'll do the comparison between the InSAR result and the seismology result. And another way is just to use the comparison is just use a single interferogram to say the result. So we are going to compare the result of using single interferogram or use multiple interferograms. Here is one example I have studied. I took the magnitude 6.3 earthquake which happened at Iran in 2018. aftershock of the large 70.3 earthquake I have shown you. And we create interference by the InSAR and the STEM software and use geckos to correct the tropospheric noise. Here we can see the first is the ascending images, which means the satellite from down to up, and the second image is descending image, which means the satellite from up to down from different look angles. Here, the star here means the epicenter of the earthquake according to the seismology, and we have choose several pixels around here. We can see the dashed line here means the earthquake happen time. We can see first it just move also some turbulence is move steady, and then suddenly the earthquake happen is directly up to down, and gradually it's just decayed, and finally it's to a stable status. And similar case also happened as a descending case, but which one is more clear? We can see here is we can see one loop is here and another loop is here. So in descending case, we can clearly say it is earthquake and we have seen it. But in the ascending case, it is much noisier and we can't see it in a single interferogram. So, but in the right hand, we use the time series analysis and we prove that because we see the gap between these two observations and we see that it's an earthquake. So we are now trying to model in the earthquakes. We can give an example here. This is a 7.3 earthquake. This is a single interferogram, and we pick a pixel here, and we see the time series analysis of it. We can see first also very noisy, but we can see it's very steady and not very change. Suddenly, when the earthquake has happened, it just jumped down to this point, which means a huge deformation, and then it's gradually form a decay. We'll see use a logarithm function to fit it, and it will finally return with time goes by. It will return to a steady case with very small changes. Future works with me will concluded more corrections to improve observation accuracy, since we can see here the observation are very noisy. And the second thing, we will use a more complicated and precise model. For example, we will consider the signal effect. And the last thing is we will use multiple earthquake modeling and departure them, because for some regions like Iran, there are many earthquakes, and we can't just use a single model to model one earthquake. We might use multiple models to model all the earthquake at the same time. So this is an earthquake in Iran, and in later we might to see the other regions like Turkey or Japan or Philippines, like other areas, to see the earthquake situation, and we will try to draw a conclusion about some general rules about this earthquake and give some insight about what I'm going to do next. So it's a brief reference. Thank you for listening.
Thank you very much. There's a lot of information there. Does anybody have anything they'd like to ask? Okay. Welcome this way.
Hello. I liked it a lot. So it might have been my misunderstanding, but I thought you were saying where some earthquakes there was too much noise, so you couldn't detect them?
Yeah.
Oh, good. Do you know if anything can be done to reduce the noise so that you can detect them, or is it a certain type of earthquake?
Yeah, right. The main error source I have introduced is atmospheric noise. It is very random, very hard to remove. Now, many researchers are trying to develop algorithm to correct its errors. I would say it's not perfect, but it works in sometimes. So that, for example, in this case, the second images, we can see this earthquake cannot be seen on the interferogram, mainly due to the atmospheric noise. So we can't see very clearly the signal like the first case. So we can try to remove more errors so that we can see them. But in some other cases, for example, like in the C case, no matter how hard you try, it's just impossible to see the earthquakes. Yeah, maybe it's too small or maybe it's too deep under the ground, so that earthquake cannot cause a various deformation on the ground, so can't see it. Yeah.
Thank you. Anybody else? I've got a question, but I feel like it might be quite a stupid one, so sorry. So these images up here are they being constantly recorded over time?
Yeah.
Okay, so then do you just sort of pinpoint random times to sort of check when earthquakes are happening, or do you wait for like a report for an earthquake to have happened and then go back? Like, how do you know when the earthquake has happened, if that makes sense?
Yeah, that's a good question, because we don't know whether an earthquake will happen. So predicting earthquake is still, I think some people believe that we can't even answer whether we can predict earthquake, no matter whether then we can predict the earthquake or not. So my study here is just to wait the earthquake happen and then back to see the interferogram of the earthquake and model it. Yeah.
Cool. Thank you very much. Anybody else?
Yeah.
Last minute. Yeah.
So, I know you're trying to predict earthquakes, but would there be other applications for this data? So, building design, something like that?
Yeah, right. Currently, for example, there are many countries when they design the buildings, they actually take into account the earthquake. For example, Japan is the case, but there. Let's see. In some countries, they are trying to design the building to prevent more damages from the earthquakes. But some countries are less affected by the earthquakes. For example, some like UK, just never maybe having an earthquake, so they will not specifically to design the building for preventing the earthquakes. Yeah, it depends on where the countries are. For example, Japan, Turkey, Iran, they might be spend.
I appreciate that, but
okay.
Can you use this data for other applications is what I'm asking.
Yeah, of course. For example, we can assess the damage of the earthquake by InSAR technique. For example, when the building is falling down from the InSAR, we can see because when the building is falling down, it will lose coherence, means it gets changed, and it was seen on the interferogram. Yeah, for example, if the change is not too fast, because InSAR have a limitation in detecting how fast it will. For example, like centimeters levels, the InSAR can detect, and above this, for example, if a building falling down and cause a meter's deformation, the InSAR cannot detect it. And currently, there are many researchers are doing the research about how to monitoring the status of the buildings, because InSAR can measure the deformation of a millimeter, and it can see whether the building has the possibility to falling down or to check the status of the building. Yeah.
Thank you very much. Anybody else before we finish? No? Thank you very much.
Thanks.